Chapter 13 of The ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Usha. The ABC of Atoms by Bertrand Russell. The New Physics and Relativity. The theory of quanta and the theory of relativity have been derived from very different classes of phenomena. The theory of quanta is concerned with the smallest quantities known to science, the theory of relativity with the largest. Distances too small for the microscope are concerned in the theory of quanta. Distances too large for the telescope are concerned in the theory of relativity. Relativity came, in the first instance, from astronomy and the study of the propagation of light in astronomical spaces, and its most noteworthy triumphs have been in regard to astronomical phenomena, the motion of the perihelion of Mercury and the bending of light from the stars when it passes near the sun. The material of the quantum theory, on the contrary, is mainly derived from small quantities of very rarefied gases in laboratories and from tiny particles running about in a vacuum as nearly perfect as we can make it. In the theory of relativity, 300,000 kilometers counts as a small distance. In the theory of quanta, a thousandth of a centimeter counts as infinitely great. The result of this divergence is that two theories have been pursued by different investigators because they require different apparatus and different methods. In this final chapter, we shall consider what bearing the two theories have on each other, and in particular whether there is anything in relativity that makes the theory of quanta seem less odd and irrational. The theory of relativity, as everyone knows, was discovered by Einstein in two stages, of which the first is called the special theory and the second the general theory. The first dates from 1905, the second from 1915. The first is not superseded by the second, but absorbed into it as a part. We shall not attempt to explain the theory of relativity, which has been done popularly so far as is possible in a multitude of books and scientifically in two books which should be read by all who have sufficient mathematical equipment. Herman Weyl's Space, Time, Matter, and Eddington's Mathematical Theory of Relativity. We are only concerned with the points where this theory touches the problem of atomic structure. The special theory of relativity, as we have already seen, is relevant to the problems we have been considering at several points. It is relevant through its doctrine that mass as measured by our instruments varies with velocity and is in fact merely a part of the energy of a body. It is part of the theory of relativity to show that the results of measurement in a great many cases do not yield physical facts about the quantities intended to be measured, but are dependent upon the relative motion of the observer and what is observed. Since motion is a purely relative thing, we cannot say that the observer is standing still while the object observed is moving. We can only say that the two are moving relatively to each other. It follows that any quantity which depends upon the motion of a body relatively to the observer cannot be regarded as an intrinsic property of the body. Mass, as commonly measured, is such a property. If the body is moving with a velocity which approaches that of light, its measured mass increases, and as the velocity gets nearer to that of light, the measured mass increases without limit. But this increase of mass is only apparent. It would not exist for an observer moving with the body whose mass is being measured. The mass as measured by an observer moving with the body is what counts as the true mass, and it is easily inferred from the measured mass when we know how the body concerned is moving relatively to ourselves. When we say that any two electrons have the same mass or that any two hydrogen nuclei have the same mass, we are speaking of the true mass. The apparent mass of an electron, which is shot out in the form of a beta ray, may be several times as great as the true mass. There are two other points where the variability of apparent mass is relevant in the theory of atoms. One concerns the fine structure and the analogy between the electron in a hydrogen atom and the planet Mercury. This was considered in chapter 7. The other is the explanation of the fact that the helium nucleus is less than 4 times as heavy as the hydrogen nucleus, which concerned us in chapter 11. On both these points, as we have seen, the theory of relativity provides admirably satisfactory explanations of facts which would otherwise remain obscure. Both, however, raise the question of the relativity of energy, which might be thought awkward for the quantum theory, because this theory uses the conservation of energy, and something merely relative to the observer cannot be expected to be conserved. In elementary dynamics, as everyone knows, energy consists of two parts, kinetic and potential. Ignoring the latter, let us consider the former. The kinetic energy depends upon the mass and the velocity, but the velocity depends upon the observer and is not an intrinsic property of a body. The result is that energy has to be defined in the theory of relativity. It turns out that we can identify the energy of a body with its mass as measured by the observer, or in ordinary units with this mass multiplied by the square of the velocity of light. Although for a particular body this mass varies with the observer, its sum throughout the universe will be constant for a given observer. However, he may be moving. In the theory of relativity, there are two kinds of variation of mass to be distinguished, of which so far we have only considered one. We have considered the change of measured mass, as we have called it, which is brought about by a change in the relative motion of the observer and the body whose mass is being measured. This is not a change in the body itself, but merely in its relation to the observer. It is this change which has to be allowed for in deducing from experimental data that all electrons have the same mass. We allow for it by means of a formula which enables us to infer what we may call the proper mass of the body. This is the mass which it will be found to have by an observer who shares its motion. In all ordinary cases in which we determine mass or weight by means of a balance, we and the body which we are weighing share the same motion, namely that of the earth in its rotation and revolution. Thus, weighing with a balance gives the proper mass. But in the case of swiftly moving electrons and alpha particles, we have to adopt other ways of measuring their mass because we cannot make ourselves move as fast as they do. Thus, in these cases, we only arrive at the proper mass by a calculation. The proper mass is a genuine property of a body, not relative to the observer. As a rule, the proper mass is constant or very nearly so, but it is not always strictly constant. When a body absorbs radiant energy, its proper mass is increased. When it radiates out energy, its proper mass is diminished. When four hydrogen nuclei and two electrons combine to form a helium nucleus, they radiate out energy. The loss of mass involved is loss of proper mass and is quite a different kind of phenomenon from the variation of measured mass when an electron changes its velocity. There is another point not easy to explain clearly and as yet amounting to no more than a suggestion, but capable of proving very important in the future. We saw that Planck's quantum h is not a certain amount of energy, but a certain amount of what is called action. Now, the theory of relativity would lead us to expect that action would be more important than energy. The reason for this is derived from the fact that relativity diminishes the gulf between space and time, which exists in popular thought and in traditional physics. How this affects our question we must now try to understand. Consider two events, one of which happens at noon on one day in London, while the other happens at noon the next day in Edinburgh. Common sense would say that there are two kinds of intervals between these two events, an interval of 24 hours in time and an interval of 400 miles in space. The theory of relativity says that this is a mistake and that there is only one kind of interval between them, which may be analyzed into a space part and a time part in a number of different ways. One way will be adopted by a person who is not moving relatively to the events concerned, while other ways will be adopted by persons moving in various ways. If a comet were passing near the Earth when our two events happened and were moving very fast relatively to the Earth, an observer on the comet would divide the interval of our two events differently between space and time. Although, if he knew the theory of relativity, he would arrive at the same estimate of the total interval as would be made by our relativity physicists. Thus, the division of the interval into a space portion and a time portion does not belong to the physical relation of the two events, but is something subjective contributed by the observer. It cannot therefore enter into the correct statement of any law of the physical world. The importance of this principle, which is supported by a multitude of empirical facts, is impossible to exaggerate. It means, in the first place, that the ultimate facts in physics must be events rather than bodies in motion. A body is supposed to persist through a certain length of time, and its motion is only definite when we have fixed upon one way of dividing intervals between space and time. Therefore, any physical statement in terms of the motions of bodies is in part conventional and subjective and must contain an element not belonging to the physical occurrence. We have therefore to deal with events whose relative positions in the conventional space-time system that we have adopted are fixed by four quantities, three giving their relations in space. For example, east and west, north and south, up and down, while the fourth gives their relation in time. The true interval between them can be calculated from these and is the same whatever conventional system we adopt. Just as the time interval between two historical events would be the same whether we dated both by the Christian era or by the Mohammedan, only that the calculation is not so simple. It follows from these considerations that when we wish to consider what is happening in some very small region, as we have to do whenever we apply the differential or integral calculus, we must not take merely a small region of space, but a small region of space-time. That is, in conventional language, what is happening in a small volume of space during a very short time. This leads us to consider not merely the energy at an instant, but the effect of energy operating for a very short time. And this, as we saw, is of the nature of action in the technical sense. A quotation by Eddington will help to make the point clear. After mass and energy, there is one physical quantity which plays a very fundamental part in modern physics, known as action. Action here is a very technical term and is not to be confused with the Newton's action and reaction. In the relativity theory in particular, this seems in many respects to be the most fundamental thing of all. The reason is not difficult to see. If we wish to speak of the continuous matter present at any particular point of space and time, we must use the term density. Density multiplied by volume in space gives us mass, or what appears to be the same thing, energy. But from our space-time point of view, a far more important thing is density multiplied by a four-dimensional volume of space and time. This is action. The multiplication by three dimensions gives mass or energy, and the fourth multiplication gives mass or energy multiplied by time. Action is thus mass multiplied by time or energy multiplied by time, and is more fundamental than either. It is a fact which must be significant that action thus turns out to be fundamental both in relativity theory and in the theory of quanta. But as yet, it is impossible to say what is the interpretation to be put upon this fact. We shall probably have to wait for some new and more fundamental way of stating the quantum theory. There is one other respect in which some of the later developments of relativity suggest the possibility of answers to questions which have hitherto seemed quite unanswerable. Our theory so far leads us to brute facts which have to be merely accepted. We do not know why there are two kinds of electricity or why opposite kinds attract each other while similar kinds repel each other. This dualism is one of the things which is intellectually unsatisfying about the present condition of physics. Another thing is the conflict between the discontinuous process by which energy is radiated from the atom into the surrounding medium and the continuous process by which it is transmitted through the surrounding medium. Relativity throws very little light on these points, but there is another point upon which it throws at least a glimmer. We find it hard to rest content with the existence of unrelated absolute constants such as Planck's quantum and the size of an electron, which, so far as we can see, might just as easily have had any different magnitude. To the scientific mind, such facts are a challenge, leading to a search for some way of interrelating them and making them seem less accidental. As regards the quantum, no plausible suggestion has yet been made. But as regards the size of an electron, Eddington makes some suggestive observations which however require some preliminary explanations. We saw that according to the theory of relativity, the interval between two events may be separated into a time part and a space part in various ways, all of which are equally legitimate and each of which will seem natural to an observer who is moving suitably. The first effect of this is to diminish the sharpness of the distinction between space and time. But the distinction comes back in a new form. It is found that the interval between two events can, in some cases, be regarded as merely a space interval. This will happen if an observer who is moving suitably would regard them as simultaneous. Whenever this does not happen, the interval can be regarded as merely a time interval. This will be the case when an observer could travel so as to be present at both events. It takes 8 minutes for light to travel from the sun to the earth, and nothing can travel faster than light. Therefore, if we consider some event which happens on the earth at 12 noon, any event which happens on the sun between 11:52 am and 12:08 pm could not have happened in the presence of anything which was present at the event on earth at 12 noon. Events happening on the sun during these 16 minutes have an interval from the event on earth which will, for a suitable observer, seem to be a spatial separation between simultaneous events. Such intervals are called spacelike. Events happening earlier or later than these 16 minutes will be separated from the event on earth at noon by an interval which would appear to be purely temporal to an observer who had spent the interval in traveling from the sun to the earth or vice versa as the case may be. Such intervals are called time-like. Two parts of one light ray are on the borderland between time-like and space-like intervals, and in fact the interval between them is zero. But in all other cases there is a separation which is either time-like or space-like, and in this way we find that there is still a distinction between what is to be called temporal and what is to be called spatial, though the distinction is different from that of everyday life. For reasons which we cannot go into, Einstein and others have suggested that the universe has a curvature so that we could theoretically go all around it and come back to our starting point in the sort of way in which we go round the earth. All the way round the universe in that case must be a certain length fixed in nature. Eddington suggests that some relation will probably be found between this, the greatest length in nature, and the radius of the electron, which is the least length in nature. As he humorously puts it, an electron could never decide how large it ought to be unless there existed some length independent of itself for it to compare itself with. He goes on to make another application of this principle which is suggestive, though perhaps not intended to be treated too solemnly. The curvature of the universe, if it exists, is only in space, not in time. This leads him to say, by consideration of extension in time-like directions, we obtain a confirmation of these views which is, I think, not entirely fantastic. We have said that an electron would not know how large it ought to be unless there existed independent lengths in space for it to measure itself against. Similarly, it would not know how long it ought to exist unless there existed a length in time for it to measure itself against. But there is not radius of curvature in a time-like direction, so the electron does not know how long it ought to exist. Therefore, it just goes on existing indefinitely. But even if the size of an electron should ultimately prove in this way to be related to the size of the universe, that would leave a number of unexplained brute facts, notably the quantum itself, which has so far defied all attempts to make it seem anything but accidental. It is possible that the desire for rational explanation may be carried too far. This is suggested by some remarks also by Eddington in his book Space, Time and Gravitation, page 200. The theory of relativity has shown that most of traditional dynamics, which was supposed to contain scientific laws, really consisted of conventions as to measurement and was strictly analogous to the great law that there are always 3 feet to a yard. In particular, this applies to the conservation of energy. This makes it plausible to suppose that every apparent law of nature which strikes us as reasonable is not really a law of nature but a concealed convention, plastered on to nature by our love of what we, in our arrogance, choose to consider rational. Eddington hints that a real law of nature is likely to stand out by the fact that it appears to us irrational, since in that case it is less likely that we have invented it to satisfy our intellectual taste. And from this point of view, he inclines to the belief that the quantum principle is the first real law of nature that has been discovered in physics. This raises a somewhat important question. Is the world rational? That is, such as to conform to our intellectual habits, or is it irrational? That is, not such as we should have made it if we had been in the position of the Creator. I do not propose to suggest an answer to this question. End of chapter 13. Read by Usha, March 6, 2021. End of The ABC of Atoms by Bertrand Russell.